So this is the part of Unit 8 that is dealing with electromagnetic waves, and we're going to start in this part because um, we finished Unit 7 with waves, so it makes sense to start with waves as well. We ended up Unit 7 with the sound waves, which are mechanical waves, and we're going to continue with electromagnetic waves. These are the waves that do not need a medium, they don't need matter to propagate. They can propagate in matter, but they can also propagate in vacuum, like space. So we have here all the electromagnetic waves, that is called the electromagnetic spectrum, and we know for sure the visible part. This is what we call light, with all the colors of the rainbow. And then if you look at the red, below the red we have the infrared, that's because it's below red. And then we have the microwaves, and to the left of that we have radio waves, FM and AM. These are the waves that you can listen in the radio. And then if you go after that, it's also called radio waves, that those big waves here, you can hear them in your radio devices. These are the longest, the ones that have the longer wavelength. You remember the wavelength is how long the wave is. That's why it's called wavelength. And the radio waves, they can be as high as as long as the Mount Everest. And we can go to microwaves that are the size of a finger or a needle, and then you're going to go to smaller scales until you get to the visible light. That's the size of a virus. And if you go to smaller wavelengths, after the violet, you find the ultraviolet, which of course means after violet. Then you have X-rays and gamma rays. This part of the spectrum is very energetic. The more you go to, the more you go to the right, the more energy you have, and so the more dangerous it is. And gamma rays are really, really dangerous. They can cause cancer almost in every organ. X-rays are also dangerous, but less. That's why you get protection every time you go to have an X-ray. And ultraviolet are also a bit dangerous, because you know, if those are the radiation that can darken your skin, and they can also provoke skin cancer, as you know. That's why you need to use protection and all that. Here you have sorry, another example of all the wavelengths with all the names. Maybe you see it's clear here, and here you can see that the wavelength is getting bigger to the left, but the energy is getting bigger to the right. I want to tell you that the sun, for example, emits in every wavelength here, in all the wavelengths, in radio, in gamma rays. And if you observe them with different telescopes that are designed for this wavelength, you can see the wavelength here. This angstroms is a unit of wavelength, is 10 to the minus 10 meters, but so you see it changes, and it changes what you see in the sun. So this is visible light, this is as we see it with our eyes, but if you use filters to see, you know, the wavelengths, you're going to see other parts of the sun, like this corona and all that. And for example, here I want to show you another example that we see different things with different parts of the spectrum. For example, this is the Crab Nebula. It's very famous because it was the one that had the first pulsar detected by Jocelyn Bell in I think it was in the 60s or 70s. Anyway, this is a nebula, and this is the remain of a supernova. So a star exploded here and created this nebula that is a cloud or so. I don't know, it's like a gas structure. And the remain of the star it's a neutron star, but we cannot see it with our eyes. I mean, if you use a normal telescope, that is the one that works with visible light, this is what you see. But you don't see the neutron star. If you use an X-ray telescope, you see the neutron star here. And you see an accretion disk, and you see the jets emitting from the neutron star here. So this is in X-rays, and this is in with visible light. So we need to study all the spectrum, because if we keep only studying this part, we are going to miss a lot of things happening. Like, for example, this. If you put everything together, it's like this. So the neutron star, of course, is in the middle, because that's the star that was born when the supernova happened. And yeah, so that's the Crab Nebula, very important one. But let's go back to the parts of the spectrum, and we as humans can feel some part of the spectrum. For example, we can feel the infrared waves with touch. We can feel if something is hot or cold, and if it's hot, it means that it's radiating in infrared. If you, for example, if you have a rainbow, like with one of these prisms, and you separate the lights, the white light in the colors, and you put a thermometer in every color, you're going to see that the temperature is going higher if you go to the red part. And right after the red, you cannot see anything, but you see the temperature is even higher. So that's why you know that there is something here, another radiation, that was called infrared, because it was below the red, and but it's here. So, and it's you can feel it with your sense of touch, because you can feel it warm. And now, because we have a lot of technology, we can make cameras to detect this infrared, and these are the night vision cameras. That's how we detect bodies, because we can feel, we cannot see them because they cannot emit light, or they don't reflect light, but they emit heat. So you can detect the infrared radiation, and then you can see them at night. We, of course, can see light with our eyes, because our eyes are the organs that are perfectly, they have evolved to see light. And so this is how you see it. So the visible light goes to the end, to the back of your eye, and there's where you form the image, and this image goes through the nerve to your brain, because you need the brain to see, of course, you need the brain for everything. But be careful, because the ultraviolet light, like ultraviolet A, also goes through and touches the nerve. So that's why it can burn your eyes. And if you burn your nerve, you're not going to see, and it has no way of solving this. If you get your eyes burned, there's no doctor that is going to make it work again. So don't look at the sun or any intense light, okay? Because if you see something with ultraviolet lights, you're going to get blind. That's why if you get and you want to go to one of these shops where you get tan, and they use this ultraviolet A, the UVA, as we say in Spanish, they put you some goggles, like glasses, so that your eyes are protected. Do not look at the sun. Do not look at ultraviolet lights. We can also feel the ultraviolet lights. We don't see them, but we can feel them, because we get darker if we are exposed to them, if we are exposed to the sun. And that's okay. I mean, you want to get tan, okay, but be careful, because the ultraviolet A can provoke wrinkles, and the ultraviolet B can make red in your, can burn your skin, basically. And here you see how much they penetrate in your skin, and is dangerous. So be careful. Also, they can provoke mutations in your DNA. That's the molecule that controls everything, like who you are, is your DNA, and yet they can break it, and that's really, really bad for you. So be careful and use protection. But going back to light, which is, remember, the part of the rainbow of the. So we have talked about the ultraviolet light in the last slide. Going back again to the part of the visible spectrum, we know that light is an electromagnetic wave. Of course, we saw that, and it comes from incandescent bodies. That means that they emit light, and they emit light because they have a high temperature. For example, you have all seen sun, of course, and you know it emits lights. But maybe you have also seen someone working with iron, and when it's really, really hot, it emits light as well. Or how a bulb works, because what you have here is a piece of metal, and you make it really, really hot, and that's why it emits light, like in this case, but with a very, very small piece of metal. Anyway, here we can classify matter according to light. So if the light goes through, we say that the material is transparent. If the light is getting through but some of it, we say the material is translucent. And if no light goes through, then we say it's opaque. Of course, this is not as simple as this, because you can have some materials that let through some color but not the others. So in this case, this material is transparent for green, but it's opaque for the rest of the colors. So the materials can depend on that. We also have that, we see in our daily life that light propagates in a straight line. But so we have seen this with the laser beam, for example, but it's not totally true, because you will see in other courses that if you have strong gravity, the light is going to bend and it's going to follow a curved path. But for a second of ESO, we're going to see that the light propagates in a straight line, and we're going to use this concept to define what a light ray is. You think this is a physical thing, but no, it's an imaginary straight line in the direction of propagation, because remember, the light is a wave, and it has this wave shape, like this one. The light is a wave, but because we see it with our eyes, and we have the impression that there are some straight lines coming out of sources, and that's why we define this light ray. But it's an imaginary straight line, okay? And then we can use it to explain the reflection in mirrors. For example, the one in here where the incident ray reflects and goes away. And for example, this happens in lakes, and we can talk about two kind of reflections. The specular reflections means like mirror reflection. If you have the surface perfectly flat, then everything is going to reflect perfectly, and you're going to have an image on something that is not a mirror, like the lake, but it looks like if it was a mirror. That's why we call it specular reflection. But if you have waves in the water, for example, it's not going to be really, really perfect, the reflection, and you're going to have different reflections. That's why you're going to see the image of the mountain, because you can see there's something here, but it's not so perfect. And we call this diffuse reflection. We have another kind of effect with light, and it's when light changes medium. Like for example, it changes from water to air, or the other way around. The light changes the direction it was going, and what we're going to see is like something is broken. And it's not that it's broken. I mean, of course, we know it's not broken. Everyone has seen this. This is refraction, and it's caused because here the light is changing the direction. In outside is air, and inside is water. So the light is going to change the direction of propagation, and the effect of that is that we see it's broken. If we are not seeing objects, but we are working with light, if we change the direction, see here, it's coming this way, and then when we change the direction, every color changes a certain amount, and that's why we have the spread of the colors, like the rainbow. And this spread of the color is called dispersion. Okay, this is the phenomenon by which waves of different wavelengths spread out as they pass through matter, the rainbow. And here you have a picture of mine in the Niagara Falls with the double rainbow. You say one here and one here, and this is all caused because of this, all the water drops that are coming from the Niagara Falls. And another effect is that we think that colors of the objects are something that is intrinsic, there is a property of the object, and it's not. Because the result of the color of an object is because this object is absorbing all the colors except for the one that it reflects. And so, for example, this red color is getting all the light with all the colors, and it's absorbing the green, it's absorbing the blue, the yellow, all the colors, and it's only reflecting red. So it's not something that it has, it's something that it reflects. That's the object. Oh, and then you have the brain working also and doing some stuff, and yeah, so it's going to be more complicated than that, and that's why you have these pictures in the internet that says which color is the dress, or which color are the trainers, or so that's because you have also the brain tricking you sometimes. And yeah. So in this case, for example, if we illuminate it with black light, that is, we wouldn't see anything because black light doesn't have red. So with green, if we illuminate it with green, this object would absorb all the green, and since there's nothing to reflect, we wouldn't see this object, we would see it as black. And I want to talk, because we were talking about noise pollution, now we have also light pollution, and this is the excess of light at night caused by human activities. As you can see here, all the big cities have a lot of light, and this is really bad for everything. For example, here you cannot see the stars, so if you look, for example, in Madrid at night, the sky is red, it's not black, it's red, and this is because we have way too many lights in Madrid. And you can say, okay, who cares about the stars and seeing the stars? I don't care. Okay, the problem is also that artificial light, which is light at night, that you don't need, and you're not designed to have light at night, because you should be sleeping when there's no light, is going to alter all your biological processes. For example, you have this hormone, the melatonin, that is the one that is associated with sleep, and you're going to change how much of this hormone you produce. And also you have some cycles for sleeping. These are called the circadian cycles, and you're going to change those cycles because you're not going to sleep when your body wants to sleep or needs to sleep. And everything is related. So in the end, you're going to have a sleep disruption, and you're going to have pathologies, you're going to have illnesses. That's why people with insomnia, they have a lot of problems with health. So not so good. I mean, it's not good for astronomers, they cannot observe, but it's also bad for people, because I mean, the negative, we can say that the negative consequences are energy waste, because we are lighting some parts of the city that are not, that they don't need to be with lights. We are damaging nocturnal ecosystems because the animals have the same problems as we do. these problems is for us humans, but also for the rest of the animals and plants. And so we are damaging the ecosystems, and also it's a problem to observe and to learn about the universe and so on in the sky. And yeah, so here you have a homework for Friday, for Thursday night, but we are going to correct it in Friday. So here I'm finishing the first video of this lesson, and then I will do the other one.